Welcome to our 35th lecture in combinatorics. So today we'll continue discussing matchings. During the last lecture, we stated and proved the Hall's marriage theorem, which states that in a bipartite graph with partite sets A and B, where size of A is at most the size of B, there exists a matching that saturates the smaller side, A, if and only if this condition is satisfied, that the neighborhood of a subset of vertices in A has cardinality greater than or equal to the cardinality of that subset of vertices S. We call this condition the Hall's condition. And we also, last time we stated the theorem on systems of distinct representatives. So if we have a collection of sets, A1, A2, AN, finite sets, a system of distinct representatives for such collection of sets consists of one element from each set, such that all these elements that we picked are distinct. Now, not all collections of finite sets have an SDR, or system of distinct representatives, and it turns out that one can characterize such sets, and we say that, and this is this theorem at the bottom of the page, stating that there exists a SDR for the sets A1, A2, AR, if and only if the condition at the bottom of the page is satisfied, namely that for any collections of sets whose index comes from a set I, which is a subset of the set 1 to n, the union of all these sets AI has cardinality, at least the cardinality of capital I. And we discussed last time, these two theorems are actually equivalent. And one can go from Hall's marriage theorem to SDR by starting with a collection of finite sets and constructing a bipartite graphs that satisfy the Hall's marriage theorem, in which Hall's marriage theorem gives you the answer for the theorem on SDRs. And one can do also the other implication. If we assume the SDR theorem to be true, we can actually get Hall's theorem immediately from it. So these two results are equivalent. Now today, what we'll do is we will do some applications of this of Hall's marriage theorem, and the first one we'll start with is discussing matchings in bipartite regular graphs. So we have a theorem about general bipartite graphs, and now we will focus on bipartite regular graphs. So let's prove. Let's do some observations first. So let's write here 1a. Let's assume that gamma is a bipartite graph with partite sets A and B, as always. And now what I want to show is the following. If gamma is k regular, so each vertex has degree k, with k being positive, then the two sides, A and B, have the same cardinality, A and B. So if you have a bipartite regular graph of valency, of positive valency, then the two sides of the graph must have the same cardinality. So if you have here, let's say this is A and this is B, and say the degree is 2. In this case, that's easy one. You have a cycle, but in general, if you have every vertex has degree k, then the two sides must be equal. So how do we prove this fact? Well, what we use is we use the handshaking lemma for bipartite graphs. So remember that in bipartite graphs, if gamma has vertex at V, which is in our case is the union A, union B, and it has edge set E, then the cardinality of the number of edges in the graph can be written as the sum over all A in A of the degree of A, and can be also written as the sum over all B in B of degree of B. Now, what is each of them? Well, because the graph, this is where you use the regularity, because the graph is K regular, then we get K times cardinality of A here, and on this side we get K times cardinality of B. So these two things must be equal. So we have K times cardinality of A equals K times cardinality of B. And because here you need K to be positive, so you can divide by it, and one gets that cardinality of A is cardinality of B. So that's pretty easy. But now what does this have to do with matching? So here's where we're heading. We would like to understand if we have, so gamma, again, A union B, E, a bipartite K regular graph, with K positive, then we actually are going to prove that the graph gamma has a matching that saturates A. Now, because of the first part, cardinality of A equals cardinality of B, if it saturates A, it must saturate B as well. So it must saturate the whole vertex set. So this such a matching is the same thing. So which is the same as a perfect matching. So any bipartite K-regular graph of positive valency must have a perfect match. So this is what we'll prove here. Okay, so how do we do that? Well, to prove that, we use Hall's marriage theorem. And we show that Hall's condition is true in every such, in any bipartite K-regular graph with K positive. Okay, so we have our graph gamma. We have the two partite sets A and B that have the same size. Okay, and so on. And now we take a subset of vertices on the left. So let S be a subset of A. So what we have to do is we have to compare the cardinality of S with the cardinality of the neighborhood of S. So we look on the other side in B, and we see the cardinality N of S. Now, what happens is that all the edges from with one endpoint in S, with one endpoint in S, the other endpoint of them is in N of S. So if I look at the number of edges with one endpoint in S and the other endpoint in NS, so this is denoted by this E of S and S, so let me write here, number of edges between S and neighborhood of S. So what happens is between S and the neighborhood of S, we have a bipartite graph with one part S and the other part neighborhood of S. But the other key thing here is that every vertex in S has cardinality K. So this expression here, the number of edges will equal summation over all X in S of the degree of X. And this is going to be K times cardinality of S. So that's one part. Now, what we're going to do, so we do the similar computation, but now we look from the perspective of the neighborhood of S. So we look now on the right, the neighborhood of S, and we look at the neighborhood of the neighborhood of S. So all the vertices in A that are adjacent to some vertex in N of S. So for example, you could have a vertex like this one here, and we have a vertex in S, which has a neighbor here in NS, and this neighbor in NS has this neighbor over here. So what is going to happen is the following. I claim that the set S is contained in the neighborhood of S. So the neighborhood of S consists of what? Consists of all vertices X in A, such that X is adjacent to Y for some Y in N of S. Okay. And clearly every vertex in S has this property because every vertex in S is adjacent to some vertex in the neighborhood of S. So that gives us this inclusion. So in picture here, the neighborhood of S is something on the left-hand side that contains the set S. Okay. So with that in mind, so we have the following. We have that S is containing the neighborhood of S. So that implies that if I count the number of edges between S and the neighborhood of S, I should get less than the number of edges between the neighborhood of S and the neighborhood of S. I think that's pretty clear. Now, the one on the left, we calculated already. This is cardinality of K times cardinality of S. This is going to be less than or equal in this expression. But this expression is the same as the number of edges between the subset of vertices on the right, N of S, and its neighborhood N of S. But by a similar argument as before, this is exactly K times the neighborhood of S. So what we end up is with this equation here, K times the neighborhood cardinality of S is at most K times the neighborhood of S, and you delete K, divide by K because K is positive, and we get cardinality of S is less than or equal than the neighborhood of S. So Hall's condition is satisfied, and that implies by Hall's theorem that there exists a matching that saturates, by Hall, saturates A, and this is the same thing as a perfect match. Okay. All right. So in bipartite irregular graphs of positive valency, we always have a perfect match. Okay. So that's one application. Another application of Hall's marriage theorem has to do with Latin squares and Latin rectangles. Let me define first what are Latin squares. So let's say n is a natural number. A Latin square of order n is a n by n matrix with entries. Let's take them to be 1, 2, all the way up to n, let's say, such that each row and each column of this Latin square, let's call it L, is a permutation of these entries, these n entries. So sometimes we will change from 1 to n to maybe 0, 1 to n minus 1. But for now, it's just in this definition, let's just deal with 1 to n. So essentially what happens is that on each row and each column, you see every possible value 1 to n exactly once. So let's give some examples. So when n equals 1, there's only one Latin square and it has one entry 1. Okay, that's easy. When n equals 2, we have two Latin squares. There's 1, 2, 2, 1. And you can change the order. You can get 2, 1, 1, 2. These are the only two Latin squares. And then the number grows. So for n equals 3, let's see, we can do 1, 2, 3, 2, 3, 1, 3, 1, 2. If we shift one direction, we can try to do 1, 2, 3, 3, 1, 2, 2, 3, 1 if we shift the other direction. And of course, you can start permuting rows and columns. So you can do 3, 1, 2, 1, 2, 3, 2, 3, 1, and so on. So you have, you could have many more possibilities. Now, okay, so what problems can we study here? Well, first of all is, are there, for any n, are there Latin squares of order n? And that's true. So for any n, there exist Latin squares. Or, yeah, I guess there exists. For every n greater or equal to 2, there exist Latin squares of order n. Okay. How do you build some of them? Well, you can do 1, 2, 3, blah, 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 n, and then you can shift. If you want to shift to the right, you get something like this one here. Well, that's shifted to the left. I'm sorry. So the one that's shifted to the right is this one here, in which you shift to the right, you get n, 1, 2, and so on, and minus 1, and so on. Or you can shift to the left and you can get this one. This is the shift to the left. So these are kind of easy ones. If you, a bit fancier, if you have a group G, a group of order n, then the multiplication table of it is a Latin square. And that's pretty easy to show. And for every n, there is at least one group of order n, the cyclic group of n elements. So that's easy. Now, what other ways are there to construct a lattice square? Well, it turns out there are many. If you want to do it with bare hands, one way of constructing a Latin square, let's say we're trying to build one of order, let's say n equals 5. We can start with our favorite permutation, 1, 2, 3, 4, 5. And then we can try to add below it something that, another permutation that doesn't, we don't repeat anything in the first column. So we can try to do, I put 2, 3 here, maybe I put a 5 here, maybe I want a 1 here. Well, in the 4, under 4, I cannot put a 4, I cannot put a 4, I cannot put a 2, 5, 1, so I can put a 2, or I can put a 3. So I decided to put a 3, and then I put a 4 here. And now, you know, what do we do next? Well, we try to repeat the procedure here. So here we cannot put a 1 or a 2, so we can do a 3. In here, 2 and 5, let me put a 4. And now I cannot put a 3, a 1, or a 4. So I don't know, let's try a 2. Maybe here I can put a 5 and here I can put a 1. So it looks like it always works. So what's happening here? Well, what we do at each step, we are dealing with what is called a Latin rectangle. So it's this one here, this one here, and the first 3 rows. So what is so if we have R less than or equal to N, R times N Latin rectangle is R by N matrix with entries as before, 1, 2, all the way up to N, such that each row is a permutation of 1 to N, and each column, so in each element appears at most once in each column. Okay, so the 3 matrices on the top, the 1 by 5, 2 by 5, and 3 by 5, they're all Latin rectangles. If R equals N, a Latin rectangle, which is R by N, it's the same thing as a Latin square. The other observation is that deleting rows from a Latin square gives us a Latin rectangle, or many Latin rectangles. But how about the opposite? So if we have a Latin rectangle, let's say we have a R by N Latin rectangle. So something like this. So this is R, this is N. Can we fill up the rest of the positions? Can we find a way to fill up the rest of the positions such that what we have here is going to be a Latin square? So the question is, can R by N Latin rectangle be completed to a Latin square? And it turns out that the answer is yes. And to do that, all we have to prove is, we'll prove the following proposition, that any R by N Latin rectangle with R at most N minus 1 can be completed to R plus 1 times N Latin rectangle. So as long as we don't have a full Latin square, so we have a kind of pure Latin rectangle, let's say, we can always add another row to it, and the new rectangle is also a Latin rectangle. Okay, so let's prove this result. Okay, so what do we have here? Well, I will do it by an example. So let's say we have some Latin rectangle here, and so this is R and this is N. I'll pick some numbers. That's a general case. Let me do the numbers here. So let me pick here 3, and let me pick here 7. So let's say the first row is 2, 1, 3, 5, 7, 6, 4. And the next one is 7, 3, 5, 2, 4, 1, 6. And the next one is 4, 2, 6, 1. I can put a 5 here. I can put a 3 here, and I can put a 7 here. Okay. So I have these 3 rows and 7 columns that I think are okay. And what I would like to do is I would like to add a new row here. So the same thing here, I would like to add in general a new row, the R+1 row, such that what do I want? I want here to be a permutation. And okay, and I don't want any repeats in these columns. So I didn't have any repeats before in the first 3 entries or R entries, but I don't want this entry that I put here, for example, this question mark cannot be one from the top column. Okay, so how do we do that? Okay, so let's give this R is our R by N Latin rectangle. And we have to think of a situation of to model it by a bipartite graph or a system of distinct representatives. Okay, so think about what is the entry here. The entry that we want to put there cannot be one of the entries from the first column. Okay, so it makes sense for us to do the following definition. So we define for j between 1 and n, let's call aj is the complement of the first column. So it's the set, you can say like this, is the set n from which we subtract the elements of the jth column of R. So in this particular case here, what would be, so let's write down what would be, let's say A4. So 4 is here, this is this column. So you want to keep there all the elements from 1 to 7, but you throw away 1 to 5. So this is the same thing as 3, 4, 6, and 7. That's the set A4, and similarly. So it's clear that this is not very difficult, that the cardinality of AJ is n minus R for every j from 1 to n. And in our case here, the cardinality of AJ is 4 for every j between 1 and 7. Okay. And now, so I said you can set this problem up as a SDR problem, but it's easier for me to think of it as a bipartite graph. And so what is our bipartite graph? So we create a bipartite graph, let's call it gamma. And we have 2 partite sets. And on one side, we are going to put, so we put on one side, we can put the elements 1, 2, all the way up to n. So in the situation that we're here below, this part A, say gamma, has the element 1, 2, 3, 4, 5. Sorry about that. 6 and 7. And on the other side, in B, we put these sets. The vertices are these sets, A1, A2, A3, A4, A5, A6, and A7. And how do we join them? Well, A4, for example, consists of 3, 4, 6. So we just joined A4 with its elements. So I join A4 with 3, 4, 6, and 7. Okay. For example, A1, what is A1 here? Well, A1 is the complement of 2, 7, 4. So A1 is 1, 3, 5, 6. So A1 is joined to 1, 3, 5, and 6. And so on. Okay, so that's the way it works in here too. You have A1, blah, 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 AN. And if we have an element here, I, we join it to a set AJ, if and only if I belongs to AJ. Okay, so then what can we say about this graph? Well, so this graph gamma, the degree of each vertex AJ is actually its cardinality, and that is n minus r. So that's easy. What about from the left-hand side? From what is the degree of each vertex? Okay, what is the degree of a vertex X? Well, this is easy to see on an example. So let's see what is the degree of 1 here in this graph. Well, if we look at the element 1, we see that it appears in this Latin rectangle in exactly 3 columns, 3 distinct columns, because each row is a permutation of the numbers from 1 to 7. So the element 1 appears in each row, but because of the property of a Latin rectangle, no element, we don't have any repeats in the columns. So we have 3 rows, so we have 3 ones, and so we're going to have 3 columns in which 1 appears. So in this case, those are the columns in which 1 appears. So therefore, that means that there are 4 columns in which 1 does not appear. And that's the first column. You see A1 here. That's a vertex which is adjacent to A1. That's the third column. So A1 is going to be also adjacent to A3. It's going to be the fifth column. So 1 will be adjacent to A5. And the 7th column. And 1 will be adjacent to A7. So what happens is this argument shows that the degree of every vertex will equal also n minus r. So what happens is that this graph gamma that we constructed is a bipartite and regular n minus r regular graph. Okay, so what? So because it's a bipartite regular graph and r here, we know that r is strictly less than n, so n minus r is positive. It means that this graph has a perfect matching. This bipartite graph has a perfect matching. So what does it mean to have a perfect matching? Well, it means there is a, so if you look at the left endpoints of these edges in the perfect matching, they correspond to numbers 1 to n, okay? And if I have, for example, an edge in the perfect matching, 1 is adjacent to A3, that means that I could put that 1 here. I definitely don't have a contradiction with the column A3. And because I have a perfect matching here, I will have no repeats in the row as well. And so that means that this perfect matching that I find in this bipartite graph can give me the column that I can place under my Latin rectangle to make a bigger Latin rectangle and to complete it. Okay, so that's that. That's how you do it, and this proves our result. Now we'll do more about Latin squares in the second semester. But now here, I just want to mention some problems about Latin. I'll go a little bit on a tangent. Some problems about Latin squares that are quite interesting. So you can construct Latin squares of order n. That's not a problem. But there's something where if the problem gets a bit more complicated if you add the following restriction. Let's say we have n a natural number, and we have a and b Latins. Well, I don't want to call them a and b. Let's call them L1 and L2. Let's say are Latin squares of order n. And we say that L1 and L2 are orthogonal if, when we look at the collection of all the order pairs of the form L1xy and L2xy for all x and y between 1 and n, this we see all possible order pairs. So this collection is the same thing as the Cartesian product of 1n times itself, 1n. So you see every order pair with entry from 1 to n exactly once. So let me give you some examples. So when n equals 2, let's say L1 is 1, 2, 2, 1, and L2 is 2, 1, 1, 2. If we look at these all these order pairs, and I'll put them here in a matrix, what we see is we see 1, 2, this one from here going here, and the 2 from here going here. And then we see 2, 1, 2, 1, 1, 2. So that implies that these two are not orthogonal, because we actually have repeats. We see 1, 2 twice and 2, 1 twice. So we have repeats. But when n equals 2, we can take the ones that we had before. Let's call them M1 and M2. 1, 2, 3, 2, 3, 1, 3, 1, 2, and M2, 1, 2, 3, 3, 1, 2, 2, 3, 1. And if we put them one on top of the other, what do we get? We get 1, 1, 2, 2, 3, 3 on the first row. And then we get 2, 3, 3, 1, 1, 2. And then we get 3, 2, 1, 3, and 2, 1. So we see everything once. So these ones are orthogonal. Okay. And now the question is a bit harder, is for any n, for what n can we construct orthogonal Latin squares? And you can get a bit more greedy, and you can denote by nn the maximum number k such that there exist L1 blah, 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 LK Latin squares of order n such that any two of them are orthogonal. Okay, so these are important parameters in combinatorics. They're related to fundamental notions such as finite projective planes. And so what we saw earlier is that n2 equals 1, and we saw that n3 is actually greater or equal to 2 because we can construct two of them. And I don't have much time, but I'll tell you about Euler, who knew all these things. And what Euler did is he showed how to prove that nn is greater or equal to 2 for any n odd. And I can give you, here's the idea. How do you construct two orthogonal Latin squares of order n when n is odd? Well, here how you can do, you take your entries, you switch from 1 to n, you switch to 0, 1, n minus 1, and you think of the entries in integers mod n, Zn. And you take L1 xy to be x plus y mod n, the addition table of that, so of Zn, so you know it's a Latin square. And you take L2, subtract x minus y mod n. And it turns out that they're both a Latin square. And one can prove because n is odd, that implies that L1 and L2 are orthogonal. Okay. Now, Euler also prove that nn is greater or equal to 2 for every n divisible by 4. So that left what happens for n congruent to 2 mod 4. And we saw that n2 is 1. And Euler didn't give the full proof, but he was convinced, he knew that n6 is 1. And this is related to what is called the problems of 36 officers from 6 regiments and six ranks. Okay, but the full proof of it was done by Gaston Tari in the 1900s. I think Doug Stinson has a paper with a shorter argument. And so 2, you have just n equals 2, you have 1, n equals 6 equals 1. So Euler conjecture that n of n is 1 for every n congruent to 2 mod 4. And it turns out that this is false for n greater or equal to 10. And this was proved by Bose, Shrikande, and Parker in 1960s. And they proved that nn is greater or equal to 2. So you can always find 2 orthogonal Latin squares for every n greater or equal to 10 and congruent to 2 mod 4. There's a big problem in combinatorics. What is n10? And so Bose, Shrikande, and Parker, they found 2 orthogonal Latin squares of order 10. And this is the best is possible. Nobody knows if n10 is greater or equal to 3. So nobody has been able to find 3 Latin squares of order 10. On the other side, I think it's known that n10 is at most 7, but this is a non-trivial result. It follows from some harder results involving projective plane and other finite geometry questions.